Okie dokie, good morning, chemists. We'll get started, jump right back into chemical kinetics. We left off talking about the integrated rate laws, so how we can calculate the concentration of a reactant with time. So, as a reaction proceeds, reactants are consumed, so we can use these integrated rate laws. So we did the calculus for you. To calculate how much reactant is left after a certain amount of time. So what we see from these equations is that K, little k, our rate constant comes out of these equations depending on how we manipulate the concentration units here, where slope is integrated into, or K is integrated into the slope somehow. Whether it's the slope is negative K for 0th order, negative K also for 1st order, but positive K for our 2nd order graph. And of course, when we graph this concentration change with time, it's only when we produce a straight line for our reaction where the data that comes out of it is meaningful. So meaning if we graph the data and we get a curved line like this, we know that this graph is not, or this reaction is not a 0th order reaction because it's graphed with the regular concentration unit. With time, it's not straight, so there's no meaningful information here. And so we'll have to regraph it just with the same data, just manipulate the concentration unit until we do get a straight line. So we'll be inspecting a little bit more of calculations using the integrated rate laws. So be sure we know what kind of order our reaction is, whether it's given in the question itself or in the unit of K. And we have to be really careful with reading comprehension and understand that in a question, there's always going to be 2 concentration units. One of them will be the initial concentration, while the other one will be the concentration after some time, given the time that's dictated in that question. All right, so that is just all the equations, so let's get back into it. We left off on slide 32, all right, where we will inspect another way to look at how fast a reaction goes via its half-life. So half-life, Counter-Strike was a core memory of mine in high school. So that's what I always think about when I think of half-life. Anyway, so half-life, the idea of half-life is the time it takes to consume half of your reactant. So the idea here is we can use our integrated rate law to calculate K, the rate constant, to consume half of your reactant, or we can use an equation here that tells us, it just spits out a time value that's related to K, the rate constant for that equation. So really, so this is for 1st order. The integrated rate law and the half-life equation here, they're actually the same equation. We've just manipulated it a little bit, and I'll show you how this works. So let's use the integrated rate law first. So let's imagine we have a 1st order reaction, and I'm giving you the rate constant, K, and you can tell that the unit is good. How long does it take for 50% of the reactant to be used up? So this is a little bit of reading comprehension. I'm asking for a time, right? I give you, so we're calculating time. We have K, and so we need to figure out what these concentrations are, all right? In order to isolate these variables where, we're only gonna calculate time, that's our one variable, we need to figure out what is the concentration after some time, and what is our initial concentration. So let's think about this. If I tell you that the reactant is 50% used up, that 50% is which concentration value? The initial one or the one after some time? After some time, right. But it looks like in this question I didn't give you the initial concentration, but can you use your kind of intuition? If we used up half of this reactant, how much did we start with? 100%, yeah, 100%. So even though it wasn't given in the question, it's implied because we're working with percentages here. All right, so that kind of makes sense. We start with 100%, now we're at 50%, now I have my 2 concentration units. I have everything I need to then calculate how much time does it take for us to lose half of our sample, so go from 100% to 50%. So we can just go ahead and stick those numbers into our integrated rate law. So natural log of 50. I'm just going to leave this in whole percentages. It doesn't matter whether you put natural log of 50, natural log of 100. You could also do natural log of 0.5 and natural log of 1. You'll get the same answers. I just like big numbers. Minus k, which is given, so 0.15. Seconds to the negative 1 time. And so we can see beautifully that there is just one variable that we need to solve for. All right, so if we do those natural log arithmetic, we get natural log of 50 is 3.91. Natural log of 100 is 4.605. And then if we do some subtraction here and put all the natural logs on one side, we get negative 0.693 equals negative 0.15 second inverse time. And now we simply just divide by negative 0.15 to get that time unit out. So time equals it's in the corner, 4.6. But what's the unit here? I know the answer's in the corner, but what is the unit of time? Seconds. Is it always going to be seconds? No, it depends on what the unit of k is. And so in this instance, because it's inverse seconds, our time that comes out is in fact in seconds. If it was inverse minutes, the time that comes out would be in minutes, all right? Okay, so there we go. That is for a first order reaction to lose 50% of your sample. And so what we'll see here for a first order reaction is if we're losing 50% of our sample, when we do that natural log arithmetic, the same number will always come out in the end. And so this is how we get our half-life equation, T1 half. The time it takes to lose half of your sample for a first order reaction is always 0.693 over k, the rate constant. So that we're just kind of simplifying it for you. We're already applying the 100%, 50% thing here, and so we can simplify this equation. And again, of course, depending on the unit of k, will give you your time unit here. The 0.693 looks like a random number, but what that number actually is natural log of 2. That's what that number is. If we do the arithmetic and the proof here, we can set A sub time equal to A sub 0, initial concentration over 2, and it simplifies to natural log of 2. All right, so that is for a first order reaction, and I'll note that all radioactive decay kinetics follow first order kinetics. So if we're referring to some type of radioactive decay, technically we don't need to tell you that it's first order kinetics. You should know that all radioactive decay is first order kinetics. But for any other type of reaction, we would have to tell you what the reaction order is. All right, so we looked at the first order half-life equation. So the time it takes to lose half of your sample for a first order reaction is that natural log of 2 over k. This is provided on the exam. Or for a second order reaction, the equation is a little bit different because the integrated rate law is different. We're not going to go through the proof here, but we see that the equation is a bit different. It's 1 over k, and your initial starting concentration is also in the denominator. So 1 over k initial concentration. So we see for a second order reaction, your half-life depends, the time it takes depends on how much stuff you start with. All of these half-lives equations, you can derive them on your own. Also, they just come from the integrated rate law. You just need to understand that, we start with, 2 molarity of stuff. The half-life equation is when your time, your concentration at some time is half of that concentration. All right, so let's do another question that, again, is a bit of reading comprehension. Okay, so here we have a decomposition reaction. It follows first order kinetics. Suppose we start with an unknown amount of N2O5, but after 11 minutes, 30% of the sample disappears. What is the half-life of this reaction in minutes? So I'm telling you it's a first order reaction. So technically, do I even need to give you the balanced chemical equation? No, I don't need to, all right? We actually will not use this equation at all. All we're going to use is the first order integrated rate law, and we will use the T1 half equation. So what a lot of students will try to do is, okay, this question is asking for a half-life, so it looks like I have to use the half-life equation, right? So T1 half is the half-life time, that's what we're calculating. So in order to calculate this, I need K, rate constant. Do I give you the rate constant in this question at all? Nope, there's no, I don't see any inverse seconds, inverse minutes, or whatever. There's no rate constant value. But I do give you a time. So what a lot of students try to do is just shove that time into this half-life equation, but we actually don't want to do that. We need to do this equation, this question, in 2 steps. The first thing we need to do is use the integrated rate law to calculate K with the given information. Once we get K, then we can insert it into our half-life equation. All right, so let's do that. So first we're going to use the integrated rate law with the information given. So our integrated rate law, we need natural log of my stuff after some time equals natural log of what I started with initially minus KT. So the information given in this question, I tell you, after 11 minutes, 30% of your sample disappears. So 11 minutes, that sounds like a time, all right? I give you a time, and I give you the amount of stuff you have left over, but again, reading comprehension. Okay, so after 11 minutes, I start with how much of my stuff? Or sorry, before my reaction, how much stuff do I start with? 100%, yes, 100%. 100% of stuff. And then after some time, this 11 minutes, how much stuff do I have left? Is it 30%? It is 70%. Yes, I lose 30% lost. So I'm actually left with 70%. All right, and so of course, you know, we start with 100, we're left with 70%. It took us 11 minutes for all of this to happen. All right, and all that information just came from what's given in the question. And so this is absolutely enough material information to shove into our integrated rate law and calculate K, our rate constant. Right, so we're going to put all this information in our integrated rate law. So natural log of 70 equals natural log of 100 minus K, that's what we're solving for, times the time it took to do that, so 11 minutes. All right, and so you do all that stuff, do natural log of 70 minus natural log of 100, and you get on the one side negative 0.3566 equals negative K, 11 minutes. And so if we divide both sides by negative 11 minutes, K is equal to 0.032, but what's the unit here? Yeah, it's in minutes to the -1 here. So it's still an inverse time unit, but it's in minutes because the time I gave you is in minutes. All right, is that our answer? Nah, no, that's not our answer. Not yet. So this is our rate constant, and so, like, to me, if I tell you, okay, a reaction has a rate constant of 0.032 minute inverse, like, do you know how fast that reaction is? I don't, personally. Okay, that number is kind of not super meaningful to me, but if I tell you you have a half-life of, let's say, 20 minutes, that kind of makes, I can wrap my head around that. I understand, oh, after 20 minutes, I'll lose half my sample. But if I just tell you a rate constant, 0.032 minute inverse, like, I don't know what that means in terms of, like, what's actually happening, what am I actually observing? So that's the purpose of half-life, to put it into perspective so we understand more. And so at this point, now that we have our rate constant, we can then now just go ahead and plug it in to the half-life equation, where it is natural log of 2 over the rate constant we just got, 0.032 minute inverse. All right, and we get that the half-life for this reaction is what? 21 minutes. 21 minutes. It takes 21 minutes to lose half your sample. So this is a two-part question. I give you some information, enough information to calculate K, the rate constant, and then I can plug it in to the rate law, or the half-life equation. We can't just do it directly because I give you time information that's not quite a half-life. Okay, let's just use our intuition a little bit here. So it took us 11 minutes to lose 30% of our sample. We just calculated it takes 21 minutes to lose half our sample. Do those two ideas make sense together? Yes, they do, right? If it takes me 11 minutes to lose 30%, to lose 50%, it's going to take a little bit of more time, right? So just make sure when we look at our answers, think, is it reasonable given the information we were given? Because if we did all this work and we calculated a half-life time of 5 minutes, would that make sense? No, because if it takes you 11 minutes to lose 30, it shouldn't take you less time to lose 50. All right, so think about it that way when you're giving responses to make sure that they're reasonable, and or it can eliminate some of the options if you can use your intuition a little bit there. Okay, so that is our half-life stuff. Okay, so we can't just shove whatever numbers we want into our half-life equation. We have to use rate constant, which often means we have to use first the integrated rate law before we do that. Okay, so just an overview of what we just talked about, the different integrated rate laws. We have zeroth, first, second. They all incorporate K and have an initial and concentration after some time. Graphically, we can determine the overall order or rate constant of a reaction if we graph it in special ways, where we see that the slope, when it's a straight line, tells us useful information, where slope here is negative K for zeroth order, negative K for first order, and second order is positive K. So if you squint your eyes and look closely, the two graphs for zeroth order and first order, they look the same, right? They both are just boop, negative slopes, right? So, when graphing these, you might be, oh, but those graphs look the same, but the idea here is that their y-axes are graphed differently. And so they will yield these different shapes depending on how you graph it. Because if it's not a straight line, it just means that we don't have a reaction that follows that specific order, however you graphed it. All right, so that is what our second way to calculate a rate law. So we did the method of initial rates, where we double something and then we see a doubling of reaction rate. That's a first order. Here we're looking at the integrated rate laws, still talking about K. We're going to kind of shift gears a little bit and talk about other ideas of K. How else can we affect reaction rate? Because up until now, when we've inspected these chemical reactions and their rate constants, we've kept the temperature the same. So if we kind of use our intuition a little bit, we know that our samples change when we change the temperature of that sample. And so what we'll see is that reaction rates also change when we change the temperature of our sample. So let's think about it to kind of get us ready for how temperature affects rates. Okay, as temperature goes up in a sample, how does kinetic energy of that sample change? It should increase. Yeah, hot samples have more kinetic energy, yeah. All right, so with that idea, if all your particles have overall more kinetic energy, how do you think the collisions change? Yeah, they go up also. If your particles are moving faster because they're hotter, they're going to collide more. So what do you think is going to happen to reaction rates when you heat it up? It's going to go higher, yeah. And so that kind of follows our intuition. When we want reactions to go faster, like if we're cooking something at home, if we want it to go fast, we just heat it up. Like, for example, I went home yesterday and threw something in the oven to get dinner ready, but then my partner texted me, he's like, oh, I'm on my way home. And I was like, crap, I need 50 minutes, this thing takes 50 minutes to heat up, but he's going to be home in 30 minutes. So I just cranked up the oven, right? We turn up the temperature to make reactions go faster. Thankfully, I didn't burn it. Yeah, so I did not follow the instruction manual very closely. I never do. Okay, so the idea here is, yes, when we heat stuff up, kinetic energy increases, particles move faster, collisions increase, and we can actually track this using an equation that we'll look at here. All right, so when you increase the temperature of a reaction, rate constant increases. All right, that's how we can change the rate constant. That's what's changing. The rate constant's changing. So K, rate constant, is temperature dependent. And so here's an example where this reaction, okay, maybe it's first order. We see an approximate doubling of reaction rate or rate constant for every 10-degree increase that we increase our reaction temperature. And so we can use an equation to talk about this, and we'll see what trends happen when we increase temperature. Because yes, the trend is, okay, hot reactions go faster, but let's be a little bit more scientific about it. Okay, so let's recall gases. All right, gases from chapter 10 and 1210, the idea that if you have a gas sample, you got a bunch of particles at a certain temperature. Are all those particles moving at the same speed? No, they have this Boltzmann distribution of molecular speeds where some of them are going fast, some of them are going slower, but if you calculate the root mean square speed, we see that overall these graphs shift to higher temperatures higher speeds when we increase the temperature. And that's because we're increasing the average kinetic energy of our sample. So just think of, we have samples where there's a kind of a range of molecular speeds. But as we heat up our sample, that range starts to push to higher boundaries. And so reactions happen when collisions have enough energy to do that reaction. So if we kind of look at this graph of molecular speeds, here we have some particles that have low kinetic energy. They're not moving super fast. So when we think about collisions between slow particles, these are slow particles, these particles do not have enough energy and don't make collisions that have enough energy to overcome the activation barrier, this hill, to do a chemical reaction. Versus in the same sample at the same temperature, there's a handful of particles with more kinetic energy than the root mean squared. So we see here these fast, high energy particles do have enough energy to overcome this activation barrier, the hill, to get over the same reaction. So the idea here is in a sample, particles are all moving at different speeds. Not every single collision will result in a reaction. It's only when there's enough kinetic energy in a particular chemical reaction for a reaction to occur. But if we have higher temperature samples, there should be a larger fraction of particles moving faster, all right? And so that's the idea of, okay, you heat it up, more particles now have enough energy to make high energy collisions to do a chemical reaction, all right? So yeah, these particles can't do the chemical reaction, but these ones, the fast ones, can. As we heat it up, we change kind of the landscape of what the Boltzmann distribution looks like. More particles have enough energy to do a reaction. Okay, so that's like conceptually what it looks like. We can also look at an equation that says kind of the same things, where we can look at trends, where we can look at rate constant here is dependent on a couple things. The first thing is frequency factor. It depends on the orientation of the collisions. This is just a constant that's specific to a reaction, right? So A is your frequency factor. It talks about collision orientation. But more importantly here, because A is a constant for a reaction, we see that K is related to your activation energy for your reaction. So what your activation energy here is in this reaction is how much energy to get over this hill. Okay, so both these reactions, they have the same activation energy. You need a collision with this amount of energy to get over that hill. So there's our activation energy. So we see that K actually increases. Reactions go faster when activation energy is low. Because if you think about it, if you were a reaction and you want to walk up this hill, Is it faster to walk up the hill when the hill is big or when the hill is small? Small, yeah, so small activation energies mean faster reactions. They'll go over the hill much faster or much easier. All right, and so the other terms in so this is the Arrhenius equation that relates rate constant to these variables, is temperature. But we already talked about this, that when we have hot samples, reactions go faster, and this equation also says the same thing. Because temperature is in the denominator, if this temperature is a bigger number, then this negative exponent becomes a larger negative value, and if you take that e to that large negative exponent, the small negative exponent, then k actually becomes a larger number. So the trend is as temperature goes up, your denominator and the exponent is larger, k overall is larger as well. All right, and then the last variable here is r. Do we remember what that is? That's a constant. That's the gas law constant. All right, so r, the r that we will use here, we've learned about two different r's. All right, one of the r's is the one we used in PivNert, so like 0.08206, but then there's another r that's related to energy, and that's the r we want to use here, 8.314 joule mole Kelvin. And the reason we want to use this r in this equation is because activation energy is an energy term. So we want to use the energy version of r. Okay, and that is how you can calculate rate constant for any given reaction. We actually will, I don't even think I assign any homework problems where I have you calculate k using the Arrhenius equation, but what you can get out of this equation are the trends that I mentioned here. K increases when activation energy is small hill, or when temperature is high, because lots of energy to get over that activation barrier. Okay, so let's talk about more details of collisions and how reactions occur. Remember, a collision is how chemical reactions happen. Two reactants collide, make a product, but not always. All right, because that collision has to, one, have enough energy to get over the activation barrier, and the orientation of the collision has to be right, I guess. Because if the two particles just kind of graze each other, it's probably not going to make a reaction, but if it's like a head-on collision, it probably will make a chemical reaction, right? So this idea, okay, we're combining two reactants to give us products. Of these four pictures, where this energy line tells you the energy of the collision, all right? I'm trying to tell you this is the energy of the two reactants colliding. Which graphs will result in a chemical reaction if you think about a single collision? Will this first one make a chemical reaction? Will you make product in this first one? Nah, there's not enough energy there, all right? This is a very weak collision. We didn't go over the hill. What about this second one? Let's give it a little bit more energy. Will this collision make a chemical reaction? No, still not enough energy to get over the hill. What about this one? Nope, still, we still aren't over the hill yet. So even this collision does not have enough energy to get over that barrier. But then finally, does the last one have enough energy? Yes, it does. Yeah, so this one, the last one, is the only one where this single collision has enough energy to get over that activation energy. Actually, before we move on, let me just clarify parts of this reaction coordinate diagram. So the activation energy is the energy difference between the top of the hill and where you start. Let's do this in a different color. So this energy is the activation energy. That's the minimum amount of energy that a single collision needs. But we've talked about these graphs before. This energy, where we start and where we end, this is not activation energy, but this we can think of as our delta H of our reaction, right? This is an endothermic reaction. Why is this an endothermic reaction? It's positive, yeah, that we end up at a higher energy state than where we started. Exothermic is the other way, where you end up lower. So in this reaction, it's positive. All right, So we have to give a little bit of energy to get this reaction to go. It's an endothermic reaction, so if we were to like hold it, it would feel cold to us. Okay, so those are kind of the parts of the reaction that we know. The new term here is activation energy. Okay. All right, so let's think more about collisions. So same idea. We're combining two reactants. Remember, it's collisions that lead to chemical reactions. So look at the different orientation vectors of these collisions and look at the temperature. Right? In the corner, you can see the temperature gauge of these four pictures. Right? But I also tell you what they are here. This one is low temperature, while number 4 over here is high temperature. Which of these collisions is most likely to form a product? Reaction 1? No, not reaction 1. Why? Low temperature. But is like the collision good? Yeah, it's a good collision, but the particles, they're moving real slow towards each other. All right, real slow towards each other. Number 2, we give it a little bit more juice here, a little bit higher temperature. The collision is still kind of head on, but it looks like there's an even better one here where there's a nice head-on collision, but high temperature, so it would be number 4. What's wrong with number 3? Number 3 is also high temperature, but what's different about that one? Yeah, it's like weird vectors. They're kind of like missing each other, so that collision isn't really effective. That's the word I was thinking for. It's not a really, so it's like, what do I want to say? Non-effective collision. Yeah, they're basically like grazing each other, and so that has a very low frequency factor there. So poor, contact, we will most likely not have a chemical reaction take place. But in number 4, we see great head-on collision, and we have a very, very high temperature. Okay, so there's that one. So for both of these examples, we looked at a single collision, where we take one reactant, the other reactant, collide them. But do we ever have samples where there's just like 2 particles? No. Gas samples, there's billions of particles. So instead of thinking of reactions taking place in these localized single collisions, we need to recognize that in an actual sample, there's many collisions occurring. Many collisions. Are the particles all moving at the same speed in a sample? Nope, you have this kind of distribution of speeds. So some of the particles will have high energy collisions, some of them are going to have low energy collisions. But if you have at least some high energy collisions, you will see this reaction proceed forward. So if we think about this sample where there's tons of reactant particles colliding with one another very, very often with time, what we want to do is look at the average kinetic energy or the temperature of that sample and recognize, okay, where that kinetic energy of that sample is will dictate whether a reaction happens or not. So just like before, but this time it's for a many collision system. If this is the temperature, there is your total average energy of your collisions. Will this lead to forming products? Yeah, the total energy is way above that activation energy. So all of these collisions, most of them are going to lead to chemical reactions. So if I just let this reaction go, I should see reactants start to form products over time. Yes. Okay, so that is for a many collision system. Let's look and compare single versus many collisions and their activation energy. So tell me. Here's a single collision, just one collision. Here is the energy of that collision. Does this lead to a chemical reaction? No. Why? It doesn't go over. Perfect. Doesn't go over. All right. Now, let's look at this many collision system. I'll remind you, are all the particles moving at the same speed? No, they're not. Here is the average kinetic energy given the temperature of this sample. Will this container lead to any chemical reactions? Yes, this one will. What makes it different? What makes these two graphs different? For the many collision system, do all of the collisions have this energy? No, some of them are actually going to be slightly higher, some of them's going to be slightly lower. But what I'm reporting to you in this many collision system is the average kinetic energy of those collisions. But we have to understand that, in a gas sample, not all of the particles are moving, moving at the same velocity. You have a small fraction of particles moving faster. So you might have a handful of collisions that actually can go over that activation barrier as long as the total average kinetic energy is high enough. In this case, we want it to be higher than the energy of the products that we want to make. All right. So yeah, in this system where there's a many collision system, we don't need to fully get over that activation energy if we're just looking at the average kinetic energy there. All right, so yes, this one does make products. Okay, so there we go, single versus many. So that's a small, actually no, pretty large detail. All right, so let's look at kind of some details and the significance of activation energy. What is activation energy? All right. Okay, so we've looked at reaction coordinate diagrams like this before. We know that where we start, these are your reactants, all right? And then we have our products over here. What kind of reaction is this? Is it endo or exothermic? Exothermic, yeah. So if we let this reaction go, what should we feel? Yeah, it should feel warm. That heat should come off. Yes, this is exothermic because the products are lower. Delta H is negative. Okay, so for the most part, we've only looked at the energy difference between reactants and products. Now we're adding this idea of activation energy. And so what activation energy is in order to go from reactants to products, all right, our reactant has to collide, our reactants have to collide in some way and distort itself, break bonds in order for it to make new bonds, right? In order to form your products, you have to break bonds and make bonds for your products. So at this high energy point of our reaction coordinate diagram, we can make what's called an activated complex, where we have this, I don't want to say intermediate species, but this species that is kind of half reactant, half product, that it has to go through in order for it to form products. So here's the idea. So like this reaction, I think what's happening is it's just a single reactant. And what's happening is that the product is swapping places the carbon and nitrogen atoms. That's what's happening. If you look at the reactant, we see nitrogen is bonded to this methyl group, but in the product, the nitrogen's now on the end. And so when we think about how do we go from reactant to product, we think about, if we were doing bond enthalpies or something. In order to make that product, I have to break that carbon nitrogen bond, but then I have to form a new bond, a new carbon-carbon bond, all right? I gotta break a bond and I gotta make a bond. And so in order to do that, this reaction, the reactant does it at the same time, where this group kind of rotates to break this bond and make this new bond. And so this species is our activated complex. It is not stable at all because you see that, okay, it's not really clear where are the bonds because it's in the process of breaking and forming new bonds at the same time. And so this activated complex exists in the high energy state of our reaction coordinate diagram. All right, okay, so let's look at this reaction, think about it. How can we go from reactant to activated complex? What do we got to do? We got to give it energy, right? So in order to get up that hill to make the activated complex, we have to give the reaction energy, like from temperature, right? Right, in order to get up that hill to make that activated complex. Do you think you can isolate that activated complex? Can you isolate it? Just think about it. If you were a ball, Okay, if I was a ball and put it right there, do you think that ball is stable? Could that ball stay there? No. Yeah, that ball's not going to stay there. It's always going to roll to either side. So no, you cannot isolate an activated complex because it's too high of energy at the top. There's no stable place for that activated complex to exist for a meaningful amount of time. Okay. Last idea here. Okay, so if we want to make that activated complex in order to make products, when is it more likely to occur? At high temperature or low temperature? What do we think? How can we get up that hill? When is it easier to get up that hill? At high temperature, yes. Because if we give the reaction more energy, more kinetic energy, more likely to get up over that hill to make the activated complex, to then go on to the more stable product. Okay, so there's our activated complex. All right, now let's think about it a little bit differently. So same thing. Yeah, so in order to go from reactants to products, I give the reaction energy, it gets over the hill to go down to products. But if we think about it, okay, I can give the reaction energy to go over the hill to products, but let's think about it. Do you think it's possible for this reaction to go backwards and go back to reactants? If there's enough energy to get over the hill backwards, the reaction can do that as well. All right, we can do the reverse reaction as long as there's enough energy to get over the activation barrier. But let's think about it. The activation barrier to go from reactants and products versus the activation barrier to go from products to reactants, are they the same energy? Nah. Which one's easier to get over? Forward or reverse? Forward. The hill's smaller to go forward, but if we want to go in reverse, the hill's bigger. All right, so let's put all these things together. So yes, the activation barrier, forward and reverse, are not the same. So now let's relate that to K. So remember the trend. K increases. Reactions are faster for small activation energies. So does that mean the rate to go forward and the rate to go reverse, are they the same rates? Nope, because the activation energies are different. So what do we think? The rates, how do the rates differ for the forward reaction and the reverse reaction? Okay, so the reaction rate constants, so K is rate constant, they're not the same because EA, or activation energy, is different in the forward and reverse. So which one is faster? The forward reaction or the reverse reaction? Just think about a hill. You want to walk up a hill. Which one are you going to walk up faster, in the forward direction or the reverse direction? The forward, yeah. So here, B, the rate constant for the forward direction is faster than the rate constant in the reverse direction. Okay. All right, so the reaction goes faster in the forward direction than it does the reverse direction. So what side, if we let this reaction go on for a while and then we went to look at it, what would be more present after some amount of time? The products or the reactants? What do we think? The forward reaction is faster, so we're making a lot of products, but the reverse reaction is slower. The reverse reaction makes what? Reactants. All right, so here, the products are going to be more favored after some time. If we just let the reaction go for a while and we look at what's left, we'll see most of the particles will be on the product side. I like to think about it like this way. Okay, the reaction coordinate diagram's like a jungle gym, all right? And all our particles are like crazy children. If you leave the children on the jungle gym for a long time, they go forward, they go reverse, they go forward, they go reverse. If you leave them there for a long time, they'll all end up on the product side because it's harder to get up the other way. All right, and I just see, they all start to accumulate on the low side of the reaction over here. All right, and so that's why products are favored due to the difference in activation energies. And we'll look kind of at the significance of this again in chapter 15. All right, okay. Where activation energy is related to reaction rates, rate constants inversely. All right, so there we go. There's our activated complex, relating it to activation energy. All right, so All right, how do we calculate activation energy for a reaction? The best way to calculate activation energy is to use the Arrhenius equation. But we have a problem, right? The Arrhenius equation that I described earlier just describes the rate constant at one temperature given an activation energy. All right, so in order to calculate activation energy for a reaction, what we need to do is look at least two reaction conditions, so the same reaction at two temperatures. So if I can calculate or determine what is the reaction rate for a reaction at two different temperatures, I can basically graph the Arrhenius equation twice to make the integrated Arrhenius equation. And what comes out is our activation energy for that particular reaction with a constant of R within there. So graphically, so in this graph you see there's 4 different data points, 1, 2, 3, 4. So this person, this scientist did the same reaction at 4 different temperatures, and what they graphed is the natural log of the rate constant at that temperature, and on the x-axis they graphed 1 over that temperature. And what they see is a straight line. And remember, as scientists, we love straight lines when useful information comes out. So if you're able to graph rate constant and temperature at more than one temperature, what comes out is the slope of this line is equal to the negative activation energy for that reaction over R. And so that's really useful for scientists to calculate an activation energy for a given reaction. You essentially need to do the reaction more than once at different temperatures, right? So on an exam, it's kind of difficult to graph stuff, give you a lot of data points. So there's another thing that we can do to calculate activation energy. 2 points will always make a line. Is that true? Yes, 2 points will always make a line. So we can basically use the integrated Arrhenius equation, but use it in, what is it called, 2-point slope form, all right? So what we can do is take the activation energy and the rate constant at one temperature, take the natural log of another rate constant of the same reaction at a different temperature, combine them into this equation, right? So this equation is what we're going to give you on the exam. This is just the proof on how to get to it. I'm not going to waste time and do it, but this is the equation that we're going to use to calculate activation energy for a reaction. And so this is what you want to look at. Okay, so natural log of the ratio of the rate constant at the first temperature over the second temperature, at the second temperature is equal to activation energy for that reaction over R. Remember, R is a constant. Parentheses, inverse the second temperature minus inverse the first temperature. So the idea here and kind of the difficulty in this equation is you need to make sure that this temperature is in the right spot with its rate constant. So K1, that's the rate constant at this first temperature, versus K2, this is the rate constant at the second temperature. So we need to make sure that our values are in the right spot here, all right? And so the units of K don't really matter because they're going to be the same units here. Activation energy will be in the unit of joules per mole because R is in the unit of joules per mole Kelvin. What do you think the temperatures need to be in? What unit? Kelvin, yeah, they need to be in Kelvin, all right? So keep that in mind. All right, so the trends on this equation. All right, I know there's a lot of stuff here, but a lot of this is kind of intuitive, okay? So if we're inspecting the rate constant at 2 different temperatures, the larger the temperature difference you're inspecting, the larger the difference of those rate constants, right? Because if you give a ton of, increase the temperature of your reaction a lot, you should see a large change in your rate constant. All right. Another idea here is that larger your activation energy, the larger your rate constant will change. with temperature. This is how I like to describe it. Okay, so if activation energy is large, what kind of reaction do you have? Is it slow or fast? It's slow. Okay, cool. It's slow. What if we have a activation energy that is small? What kind of reaction do we have? It's fast. Okay, cool. So if I give a little bit of extra heat, temperature, to these reactions, do they go faster? Yes, they do. But which one changes more? All right? So in the reaction where the reaction is already going slow, it's already going slow, and you give it more energy, it's going to take that energy and go a lot faster because it's already going slow. Versus a reaction that's already going fast, you give it a little bit more energy, it goes faster, but not as much because it's already going fast. The analogy I like to use is, okay, so pretend money is energy, okay? If you give me $1,000 versus if you give Jeff Bezos $1,000, for whom will it make a larger difference? For me, because my reaction is already going slow. If I get $1,000, I can do a lot more with that money. Versus if I give $1,000 to Jeff Bezos, he already has a ton of money. It's like a drop in the bucket. But does Jeff Bezos become richer if you give him $1,000? Yeah, but is it going to make a difference? Not a big difference. And so if you're already going slow and you give more energy, it's going to take that energy and make a larger difference. And that's kind of just the consequence of how this equation works. With the natural logs and the 1 over temperature, if activation energy is already large, you're going to see a bigger difference in your K1, K2 ratio when you calculate this equation. All right, and so that's a big idea. All right, I think I talk about it here. Okay. All right, so reaction 1 is exothermic. Do you agree? Yes, because it goes overall downhill. Reaction 2 is endothermic. Do you agree? Yes, because it's overall uphill. Do they both have activation energies? Yes, they do. So let's compare them. Which one has the larger activation energy? Reaction 2. Yes. C to D has the larger hill than A to B. Assuming that I made this all proportional. Just assume I made it proportional. All right. Okay, so then, therefore, we got that reaction 2 has the larger activation energy. Which reaction has the larger K value? Or which one is faster, reaction 1 or 2? Reaction 1, okay, perfect. All right, so then let's answer this. Think of Jeff Bezos giving $1 to me versus Jeff Bezos. If we increase the temperature, what happens to the rates of reactions 1 and 2? Do they both get faster? Yes, but which one changes more? Reaction 2, yes. So let's look through the wrong answers. A is incorrect, where, okay, yes, both reactions increase, but you're incorrectly assuming that they both increase the same amount. All right, they don't. They don't. Versus both reactions increase, but reaction 1 increases more. That's not correct either, because reaction 1 is already going fast. So if you give it a little bit more energy, yes, it's going to go fast, but the ratio is smaller. Versus both reactions increase, but reaction 2 increases more. All right, that would be the correct answer. D is not correct because I'm saying one of them decreases. That never happens. Right? Increasing temperature will always increase your reaction rate. I have another analogy. When I was in high school, I had to sign up for like a gym class. And so I picked weight training because I thought it'd be easy. And on the first day of weight training, they made us do like our calculated 1 rep max, all right? On the first day, because part of your grade was to like improve during the year. All right, so part of the our letter grade was what percentage did you improve throughout the year in your like 1 rep like bench press. Yeah, imagine me bench. So me, okay, first day I could barely pick up the bar. How heavy's the bar? It's like 45, 50 pounds or something like that. Yeah, I could barely pick it up. I think I did it like 3 times or something. But then there are other people in my gym class that they went crazy. They were like trying to impress one another. So their 1 rep maxes were like in the 200s, 200 pounds. Well, mine was like barely 50 pounds, you know? So as the semester goes on, like I'm able to put like 2 10-pound weights on the sides, all right? Like I only improved a little bit, but if you take the ratio of how much I improved, I basically guaranteed myself an A by just putting on like an extra 10 pounds of weight by the end of the year, versus the people who already started at 200, in order to get the same ratio, right, the same percentage increase, they had to add 50, like 100 pounds to their barbells, and that's just like not feasible for them, all right? So the people who already started fast, they couldn't improve as much as me because I already started slow. And so there's another analogy there, okay, that again, adding temperature always increases reaction rates, but if you're already going slow, so high activation energy, you increase more, right? I didn't think of that when I took that class, but it just happened very nicely in the end. Okay, all right, so this is the last question before midterm 1 material ends. Yes, okay, so. All right, so here's a question. We study a reaction at different temperatures and its rate constant. We note that the rate doubles when the temperature increases from that to that. What is the activation energy? So I showed you a bunch of equations with activation energy in it, so we need to make sure we choose the right one. And so this is your strategy. I give you 2 temperatures, don't I? So don't we want an equation with 2 temperatures? And we want an equation with activation energy, but technically, you know, most of these equations have activation energy in it, but we just need to make sure we choose the right one. So do we use the Arrhenius equation? No, because there's only 1 temperature. Like if I gave you 1 temperature and the activation energy, you could calculate K, but that's not this question. Do we want to use this equation? No, that's the integrated rate law. No, there's no activation energy there, right? What about this equation, the 3rd one? Do we want to use that one? Yes, that's the one we use because it has 2 temperatures. We don't need to use the last one. That's one where if we would do it graphically on a graph, that's the equation we would look at, because if this follows y equals mx plus b, a straight line to get that information out. But since we just have 2 temperatures, 2 reaction rates, we're going to use that 3rd equation. This is the one that we give you on exams. Actually, I think we give you all of these. But again, it's being cognizant of which equation do we use. Okay, so we're using the 3rd equation, but we need to put in the numbers. So this is, again, reading comprehension. Okay, the temperatures, yes, I have 2 temperatures. We're going to need to put these in Kelvin, so I'll just put that in Kelvin right now. So we have 293 Kelvin, and then the other one is 333 Kelvin. But we need to be careful, right? Okay, so we have temperatures. We want to calculate activation energy, but we're not really explicitly given our rate constants. So we need to be smart about it. Let me just go ahead and define our variables. I'm going to call T1 293 Kelvin, and I'm going to call T2 that 333 Kelvin. We need to figure out what is K1 and K2 at these temperatures. So we got to use reading comprehension. I don't tell you the rate constants explicitly, like I don't tell you numbers, but what do I tell you? Rate doubles. So just make up a number. Let's say K1, the rate constant at 293 is 1. What is the rate constant at T2? 2, yes, it is 2. Do the units really matter? Not really, because we're just going to divide them by one another anyway. All right, so from that information, the ratio here, we were able to get what is that K1, K2 ratio. From the information, the rate doubles. Yes, I could have given you values, but this one I like because it requires a little bit more complex thinking than just plugging and chugging. So at this point, we have K1, we have K2, we have T1, we have T2. We have enough information to calculate activation energy. We just need to be careful about where we place K1, K2, T1, T2. We just got to be really careful. I promise you will make mistakes. So it is natural log K1 over K2. So what is this fraction? 1 over 2 equals activation energy, that's what we're solving for, over R, so 8.314. I'm not going to write the units out. You know it's a joule per mole Kelvin. And then inverse T2, so which temperature? It's the 333. So 333 to the -1 minus 293 to the -1. So do be careful of those variables, because if you swap these two, you'll get a wrong activation energy. All right. Okay, and so now it's just a bunch of arithmetic to isolate activation energy. So natural log of a half is -0.693 equals activation energy over 8.314. If I do the inverse temperatures and subtract, I get -4.099 times 10 to the -4. If I divide both sides by this parenthesis, multiply by R, we get that activation energy equals 14053. You solve, isolate activation energy. Okay, so what unit does that have? Yeah, it's just joules. Joules, because R has the unit joule mole Kelvin. So that means activation energy is in the unit of, it's actually in joules per mole. All right, but that's a really big number, so it's probably best to report that in a kilojoule amount. So yeah, 14.1 kilojoules per mole is our activation energy. All right, and so this is an example of the rate constant at two different temperatures is enough information for us to estimate our activation energy, because 2 points will always make a line. Of course, we could get it better if we did it graphically, where we did like 4 different experiments at different temperatures to get a straight line and inspect the slope there. All right, so that is the last part of midterm 1. All right, so we got like 20 minutes left. I'll remind you that reaction rates, so us using stoichiometry to say, oh, if I consume, this much reactant per second, I should also observe producing this much product per second. For example, we can just use stoichiometry. We looked at rate laws and rate constants, method of initial rates. That's how we can experimentally determine a rate law. Then we looked at the integrated rate laws, where graphically, depending on how we graph the data, we can figure out a rate law, whether it's first, second, or 0th order, and we can calculate the concentration at any given time. And then the last section here, we looked at temperature and rate, activation energy, how that relates to K, our rate constant, and collisions, and all of those trends are within the the Arrhenius equation. All right, so that is midterm 1 material. Remember, chapter 14 is split up into 2 sections. So that means that the first part that covers this material, sections 14.1 through 4, is due on Monday. All right, and then the second one, the second set, won't be due until we finish this section, probably next week. But yeah, midterm 2 will include reaction mechanisms and catalysis, so do keep that in mind, but we still have to barrel forward with this material. But if anything, we can appreciate that now we can look at the last way we can get a rate law, and that is reaction mechanisms, and it's, I think, the most fun way to get a rate law. And so the idea is, yes, collisions result in chemical reactions to make products, but we can think about those collisions in singular, simple steps. If you think about, like this could be a reaction. You take parts, you take workers, maybe tools as a catalyst, and you make products. So in this case, bikes. But there's a lot of intricate steps involved in that, right? It's like, I'm teaching 1250, and which is chemistry for engineers, and so they like had their first lab, right? And we were teaching them to write a procedure, and so one of the procedures that I read there for WRM was literally make worm, destroy worm, and that was it. That was their procedure. Yeah, I know you laugh, but you guys have experience, right? You're like, oh no, there's a lot of other little steps within there. You can't just like make a worm and then destroy the worm. And I made the analogy, it's like if you go to a cake recipe, you look up how to make a cake, and you read the recipe, it just says make cake. Is that a good recipe? No, there's a lot of little intermediate steps there, and that's what we want to think about in terms of chemical reactions. There can be little steps involved for a chemical reaction to occur, and that is called a mechanism, right? Where we are inspecting all the little steps to go from reactants to products, because from like up until now, yes, our recipes have just been make products or make cake, and that's it. So now we're going to look at all of the little steps to get there, right? Reactions don't have to happen in one step. They can happen in a step-by-step pathway to get to products, right? So here's an example. So here is a reaction mechanism. It's a little bit more complex, but see how there's two humps? There's one step, right? There's one hill, but then there's another hill. And so this reaction is happening in two steps. So we can tell you those steps. I can say, oh, you combine A and B and you get this thing, AB, compound AB, but then AB reacts with another B atom to get BAB. And so if we take these two steps and add them up, like Hess's law, we see that one of the species cancels out. Which one cancels out of this reaction? AB, right? AB is produced but then consumed in the next step. And so we see the reactants and products that are left over. That is our overall reaction. We've always studied the overall reaction. So now we're unveiling the curtain. Okay, this is what's actually happening behind the scenes. This is happening in a two-step pathway, but those individual steps have to add up to the overall reaction that we've always known. And so the idea of a mechanism, remember, we can't see atoms. So when we propose a mechanism, it's just a proposal, because technically I can't see every collision that happens. This is just my best guess at what the mechanism is. All right. Okay, so the great thing here is that the steps that we propose need to add up to the overall rate law, but the mechanism also has to agree experimentally with rate laws that we talked about in the previous chapter, or previously in this chapter. Like if I know that this reaction is a first order reaction with respect to something, I need to make sure my mechanism matches that as well, and that's what we'll talk about here next. All right. Okay, so remember all this time when I told you, okay, if I wanted the rate law of this overall reaction, can I just take the coefficients and make them exponents? Am I allowed to do that? Nope, you can't do that, right? All rate laws have to be determined experimentally. But with mechanisms, now we are allowed to do that, okay? So if I tell you a mechanism for a reaction, I'm giving you the individual steps. So for each of those individual steps, now you are allowed to just take the coefficients and make them into exponents. Only for mechanisms, only for mechanisms. So here's some examples, all right? If I have a step that just has A as a reactant, the rate law for this step is just A to the 1. If I have an elementary step that combines two A atoms, the rate law for that step is A squared. If I have AB combining in it one elementary step, I am allowed to just, say rate equals K AB. right? So for elementary steps, you are allowed to take the coefficients and turn them into exponents to get your rate law. But those are for the individual steps, right? And what we'll see here is that we have to kind of manipulate these steps to get the overall reaction order, and we'll talk about that in a little bit. All right, and so the molecularity of these elementary reactions just counts the number of particles interacting in each of these collisions. So an elementary step is a single collision that's happening. Two A particles are combining. So that molecularity is bimolecular because two molecules are involved. 3A particles colliding with one another, that's termolecular, meaning three particles are combining. Statistically, that's not super common. Usually unimolecular or bimolecular single steps are more common because the likelihood of 3 or 4 particles all colliding at the same time is very unlikely. So we're usually going to see unimolecular and bimolecular elementary reactions. So yeah, these two are common. Actually, no, all three of these are common because all three of these are either uni, this one's uni, this one's bi, that one's bi as well. Termolecular, not super common, and especially like tetramolecular, you'll never see that. 4 particles colliding at the same time, nah. Okay, so now with elementary steps, we can, in fact, just turn those coefficients into subscripts. So let's do that. So here, I give you a mechanism for a reaction. Here are the individual steps. So each of those steps are an elementary reaction. So first, let's get the overall reaction. So how do we do that? Just add it up. Yeah, add it up, cancel some stuff out. So I like to think what cancels. Look at the product side and the reactant side on the other equation and see if we can't cancel anything. Okay, so what cancels? HI cancels, yep. That cancels. Anything else cancel? No, that's it. So now we just add stuff up. So it looks like we have an H2 combining with 2 ICLs to give I2 and then 2 HCl's. Cool. All right, so this reaction, like this is what we would inspect using stoichiometry, but what's happening behind the scenes is 2 different collisions, 2 different steps are happening. That an H2 molecule and ICl are colliding to make an HI particle, but then that HI particle gets consumed in the next step, so we actually never see it in the product. Okay, so that's the overall reaction. What is the molecularity of each step? So what do? We just count the number of particles involved in each of those collisions. So step 1 has how many particles? 2. 2 things, boop, are combining. And so step 2 is also bimolecular. So yeah, 2 particles, so both of them are bimolecular. And that's common. All right, let me just erase the things that canceled in our reaction. So let's determine the rate law for each step. So what do? What do? Coefficients become superscripts or subscripts? Superscripts. Am I allowed to do that? Am I allowed to do it? Yes, I can do it for only elementary reactions. And because I'm telling you that these are individual steps, we can do it. So for step 1, the rate law for just that step is K. I'm just going to call it K1 because this is the K for step 1, is H2 concentration times ICl concentration. That's it. We're allowed to do it. Then step 2, it's going to have a different rate. So I'm going to say that this is K2, rate constant 2. It's a different value. I don't know what it is, but it's okay. Will depend on the concentration of HI times the concentration of ICl. And that's it. And then finally, identify intermediates. So an intermediate is something that is produced in a reaction, but then consumed in a later step. So an intermediate is something that you never see as a product, but is still created during the process of the reaction. So what substance is an intermediate here? It would HI, the thing that we canceled out, yes, is our intermediate. Okay, so the easy part is getting the rate laws for the individual steps. But is either of these the rate law of the overall reaction? Not quite. So that's what we're going to go into next. We just got the rate laws for the steps. Now we need to decide, how do we get the rate law for the overall reaction? It's not that bad, right? This is the big idea. The slowest step in the mechanism is what we call the rate determining step. It's the slow step that determines the overall rate law of the reaction. The slow step determines the rate law of the overall reaction. Usually we have to tell you what the slow step is. Okay? And so we're going to look at two ways to study mechanisms. We're going to first look at the easy one, where the first step is the slow step. And then we'll do a slightly harder one, but it's not that hard, is where the slow step is the second step. All right? And so depending on where that slow step is will change how we perceive the overall reaction rate. All right? The slow step determines the rate law of the overall reaction. So let's go back to this proposed mechanism. If I tell you, okay, this is my mechanism, it's two steps, step one, step two, and I'm telling you that the first step is the slow step, what is the rate law for the entire reaction? It is the rate law for the slow step. It's the first step. So it's the rate of that step will determine the overall rate of the entire reaction. So simply, this reaction, because the first step is the slow step, the rate equals K1 times A concentration times B concentration, and that's it. That's it. Right? And so we're allowed to take coefficients and make them exponents because each of these steps are elementary. Slow step always determines the overall reaction rate. All right? Okay, and so this is what the reaction coordinate diagram would look like. You can see that, yes, that first step is the slowest step. How do we know that? Has a big hill or large activation energy. So this step is the slowest step. That's our rate determining step. And so what we see here, I mentioned it before, AB is an intermediate because it's made and then consumed later. If we look at this reaction coordinate diagram, AB would live kind of in this crest between the two steps. AB would exist between those two steps there, but it would be consumed before making products. Okay, so we have time for this one question because its first step is the slow step. All right, so tell me, here's a reaction, there's the proposed mechanism. Which step is the rate determining step? It's the slow step, yes, it's the first step. So do we really care about the second step? No, we don't care about it at all, right? It's not going to affect our overall rate law. So the rate law for the rate limiting step, so this is the slow step, is equal to rate equals K, I'm going to call it K1 because it's step one, NO2, oh, NO2, so it's just NO2 squared, there's two of them, boop, that's it, boop. All right, so that is the rate law for the slowest step. So what is the rate law for the entire reaction? It's the same thing. And the only reason we can do that is because the slow step is the first step. K1, NO2 squared, right? And so what we see is that this reaction is second order in respect to NO2, but look at the overall reaction. It's NO2 plus CO gives us products. So based upon what we just learned, if we did this reaction and let's say doubled the concentration of CO, carbon monoxide in this reaction, should we see a change in reaction rate if we change the concentration of CO? No, because CO is not in the rate law at all. All right, and we got that via the mechanism. All right, so we'll come back to this next week. So remember, the first part of chapter 14 is due on Monday at midnight. All that material is on your midterm next Friday.